Assalamu alaikum, dear students. Today in this lecture, we are going to discuss Argand plan and polar representation of complex numbers. As you know very well that for every complex number, we have two parts, that's the real part and imaginary part. And to represent any complex number, we need two axes, that's real axis and imaginary axis. So the plan, while we represent this complex number, that's called complex plan or Argand plan. So how to represent that? Along this horizontal axis, that's also called as the real axis, we represent the real part of the complex number. And along this vertical axis, that's called the imaginary axis in the Argand plan, we represent the imaginary part of the complex number. So in order to represent the complex number, we have the modulus that has already been defined. So how can we define the modulus of a complex number? The modulus of a complex number x plus I times y, where this x is the real part and y is the imaginary part of the complex number, that's equal to under root of x square plus y square. Okay, whenever we measure the distance from the origin, however, it is if it is deviated from the origin, that can be measured accordingly. But for the sake of simplicity, we may be taking the distance from the origin. Okay. Once again, I would like to repeat here that x-axis and y-axis in the Argand plan are respectively called as real axis and imaginary axis. For example, we have a point that's P of x comma y, and this is origin, and that's point of intersection of the real and imaginary axis. You see here in the first quadrant we have a triangle, and whatever we'll be going to discuss, that is in light of this triangle. Okay. You see now we will be representing the complex number on the in the polar representation. So we will be discussing here polar representation of a complex number. For that, we have to discuss two things. One is modulus of a complex number, that's defined earlier, and next is argument, principal argument of the complex number. So you see this triangle that has been displayed earlier here. In this triangle, you see we have, this is a distance along x-axis and this is distance along y-axis. So this is here x units and this is here y units, and this is y units along y-axis, this one. Okay, and what is this distance between origin and p, that is 0 0 and p of xy, that's called the modulus of the complex number. Okay, so here it is. If you will complete the triangle, and you will see here, we will draw a perpendicular from this, and we will go to the different trigonometric ratios that can be calculated from this. You will see that we can calculate x is equal to r times cos theta, because if you will define cos theta from this triangle, if we complete this triangle, you will get cos theta is equal to base divided by hypotenuse. Base is x and hypotenuse is r. That's modulus of z. R is actually the renaming, or it is a symbol that represents modulus of z. So you see, by the definition of the cos, we have x is equal to r cos theta. And similarly, y can be defined as r sin theta, because you know sin theta, if you want to define, that's equal to, that's perpendicular divided by hypotenuse. So y is equal to r sin theta. Okay. So if we will put this x and y in the given complex number, x is equal, z is equal to x plus iy, you'll see that z is equal to x is r times cos theta and y is equal to r times sin theta. So it's r times cos theta plus I times sin theta. Okay. So in the different quadrants, you can take this accordingly. The angle described by this modulus of the complex number, that is here, you see this theta is called as the augment. Okay, that has the angle that is described by the modulus of the complex number. So for any complex numbers that are not equal to 0, there corresponds one and only one theta in 0 to 2 pi. What is the 0 to 2 pi? That's actually the one period, one complete rotation. So in this, for every theta, there is one and only one complex number. Okay, so I mean to say, for any complex number, there corresponds to one and only one theta in the range 0 to 2 pi, but the converse is not true. Okay, so we may, however, any other interval of length 2 pi, for example, this can be such an interval. That means we can write this interval in other form also, that's minus pi to pi. So we'll take it from minus 180 degree to 180 degree. That also measures the same, that is 360 degree angle. So we shall take the value of theta as minus pi to pi. That's called as the principal augment, okay, of the complex number, and that's usually represented by ARG of Z. Okay, so let's see here one example that makes things clear. We have to represent this in the polar form. So in order to represent this in the polar form, we know the polar form of the complex number is Z is equal to R times cos theta plus I times R sine theta. So we will take here the given complex number. In this, the x component is 1. So R cos theta is equal to 1, and y component is under root 3. So under root 3 is equal to R sine theta. Okay, if we'll square and add these, we'll get R is equal to under root of under root 3 square, that is 3 plus 1, that's 4, that's 2. Okay, therefore this cos theta is equal to 1 by 2 and sine theta is equal to under root 3 divided by 2. Okay, and if you want to find theta, how can we? Theta can simply be found by dividing these two equations, and how it is R sine theta divided by R cos theta, that is R and R cos, tan theta is equal to, tan theta will be equal to under root 3 divided by 1. Okay, so theta is equal to pi divided by 3. So the required polar form is equal to, here it is the value of R, and here it is the value of theta. So it's R times cos theta plus I sine theta. Okay, so this is the polar representation of the given complex number. On the same lines, we can write this. First of all, we have to change it in the standard form, as in the previous exercise. After that, we will change its form in the polar representation. Okay, so this way we can solve these questions. So here's question number 1 of exercise number 5.2. So we can find its modulus, and we can find its augment here also. So on the same lines as in our exercise, we can find the modulus and the augment of the given complex numbers. So on finding the modulus and the augment, we can write the value of the R and theta in the polar representation, and we can find the polar representation of the given complex number. So if you have any questions, you may ask in the comment section. Thank you for joining the class.